to this new YouTube channel, the Spark Research YouTube channel. I am Dr. Vichandra, and here we are going to talk about the course VLSI Design and Technology. So in this session, we are going to learn about the more than 70% part of Unit 4 and 5. So this is the definitely application based, that is the how can we fabricate a device. We are going to consider the CMOS inverter in this session, but this is the conclusion of the unit 4 and 5. So why are we talking about the VLSI fabrication first of all? Like, because our objective is to fabricate a VLSI devices. So how can we fabricate? So here we are going to consider the example. As an example, we are going to consider the CMOS inverter. Inverter means, if you remember the logic circuit design that we have already discussed in the previous session, then CMOS logic style consider the two different MOSFET. What are that? Combination of N type of MOSFET and P type of MOSFET. So our objective is to design the CMOS inverter which includes both, that is N MOSFET and P MOSFET on a same VLSI design chip. So let's start. How can we fabricate? So step number one, in order to fabricate the CMOS inverter, first we need a base material over which we can fabricate. So the base material is called the substrate. Substrate, now what type of substrate we can consider? Substrate may be either P type of silicon wafer or maybe the N type of the silicon wafer. Now how will we choose? So P type means if we are going to design the N type of MOSFET, then P type of substrate we can select. Or if we wanted to design the P type of the MOSFET, then we can select the N type of the wafer. So this is just a wafer. Now first we will go for the RCA cleaning in order to remove the contamination. So this is the step one, that is called the substrate preparation or wafer preparation. So after completing the base, that is this one, now we'll go for the well formation. Well formation may be the multiple types, but here how can we create the well? So here suppose the P well and N well, right? Or maybe the N well, P well. So why are we creating these two different wells? Because this is the well in which we are going to design the N MOSFET and P MOSFET. Similarly, if you wanted to design the multiple MOSFETs, then you can create the multiple well. So here, since we are considering the example of inverter, which means we need two MOSFET and MOSFET, P MOSFET. So now these will act as a substrate for our P MOSFET and N MOSFET, right? So now question is that how will we define P well and well? How can we create it? So we'll use the photolithography to define well regions. These. So how we'll do this photolithography? So in unit 4th, it has been extensively covered, that photolithography. So photolithography is nothing. Use light as a source. Light means UV light, and mask. Mask will be like used to design the particular this pattern. Now who will create this pattern? So photoresist, and then expose the UV, and like depending on the photoresist where you have kept, the mask will design create the patterns on this substrate. So this is the summary of the photolithography. I repeat, photolithography, it means you need three things. What are that? First, UV laser source. Second, mask. Third, photoresist. And final is your substrate over which you are going to grow. So these one. Now the how can we create the exactly the P well and well. So phosphorus you can select in order to design the and well, and like the fifth group elements, like this is the doping concept only. If you know the doping, then you can do. So ion implementation means, so you have the like four in your silicon, pure silicon. So how many electrons are there in outermost orbit? Definitely four. So phosphorus have the five. So if we are going to ion implant this phosphorus, definitely it will be the N well. So similarly, you can select the P well. Now after completing this lithography, now the your substrate, your device is ready, the first layers is ready. But if there is some variations in the dopant, then in that case, to repair your device, you can use the annealing process. So this is the annealing. Annealing is the repair. If you wanted to repair the dopant, that is the you wanted to make it uniform, because there may be the not uniform placed of your p-type n-type because of the some void, or maybe the because of the multiple regions in your crystal. So how will you repair the crystal? Using the annealing method. So annealing is what? Just raise the temperature and cool down. So that's called the annealing, nothing. So these type of questions will also come. What is the photolithography, then what is the annealing? So these are the summary about this. Then next step, like isolation, shallow trench isolation, ST1. So you are going to isolate both. If both will combine, then definitely it will not work. So how will you do that? So trench etching using dry etching. So whatever the regions, whatever you have already patterned using the photolithography, if you wanted to remove the some area, like if you wanted to make the some regions which should be filled by the SiO2, and so how will you do that? So first, in order to remove the anything, you can use the etching technique, right? And each after performing the etching, means if you wanted to remove the some unwanted layers, then you can perform the etching. So etching may be the different types, like how will you do dry and wedge etching? So dry means you are going to use the like gaseous, like chlorine, fluorine. And wedge etching means you can use the some chemical, the liquid type, right? Like HF. So these are the different types of the etching. So now etching is also covered. Okay. So after performing the etching, you will have these type of patterns. So here, if you see, then we know we have already discussed about the wafer preparation, then photolithography, then ion implementation, then annealing, then etching. So all these things step by steps we have discussed in the unit 4. So these are the topics, right? Now continue to talk. So now how will you develop the gate of this your N MOSFET, P MOSFET? So in order to develop the gate, now you should go undergo with the thermal oxidation process, that is called oxide formation. So again, how will you do? Exactly with the help of the thermal, that is the high temperature, you are going to develop, that is Si plus O2, that is SiO2. Here it will grow in the high temperature, it will grow. Now definitely you have to use the the layers, then the polysilicon layer over to this your gate. Now if you wanted to develop the polysilicon layer, that is the exactly the gate material, means after the oxidation process, oxidation means SiO2 layer, then if you wanted to develop the silicon layer over this SiO2, how will we do? We can use the LPCVD, chemical vapor deposition technique. So deposition technique will be used. So here again you can use the photolithography and then the etching technique. Suppose if your reason is like height is higher than the width is higher, or whatever, you can use the etching technique after the deposition. Okay. So this is the here is the deposition technique. So deposition technique is to use to develop to grow the polysilicon layer over the gate oxide layer. And how can it be done? Definitely it can be done using the photolithography. Again the same process, photolithography, that that we have already discussed. So that covers all these topics. Okay. So at the end of this, like lightly doped drain, then you have to also develop the drain and source. So how can we develop? Using the ion implementation, we can develop the drain and source. Also, we can use the diffusion technique. Then space formation. So deposit SiO2 and Si3 and 4. That is the space formation. That is green color one. Here you can see. So perform anisotropic etching to space around gates. Anisotropic, what is that? Etching is two types of the etching: anisotropic and isotropic. Isotropic uniform, and isotropic like not uniform, like these types of circles. So this is the two types of the etchings, right? Then source and drain, that is the use of photolithography to expose the active region. Active region means where do you want to develop the gate and drain. So you can use this the ion implantation and perform the RTA for dopant activation. RTA is your rapid thermal annealing, right? So already we have covered. So now solicitation, that is the contacts. How will you provide the contacts? So definitely we can use the the rapid thermal process, and then after all performing all these, we can use some metals to perform the the contacts, to develop the contacts among all the layers. So how can we do metallization technique only? What type of the metals can be used? So it's depending. Normally we can deposit the nickel, titanium, like that, depending on the type of the application. So interconnection, that is deposit multi-layer metals like aluminum, copper using the PVD or CVD, chemical vapor deposition, or a physical vapor uh, deposition. Okay, and then use CMP and persuasion layers for protection. So this is the protection. Finally is your annealing and testing. Annealing is just to perform to check whether is there any crystal defects or not. If it is so, then you can perform it by increasing the temperature. That's all the about the annealing. And then the electrical testing, like just check, apply the voltage and whether current is flowing or not. That is the testing. So this slide is the overall summary of your unit 4 and 5. So here is your substrate, that is P silicon normal, and this is the anvil. Anvil means you are going to design the P type of MOSFET. So here this is your drain, here this is your source, and this is your SiO2 layer that it can be developed using the oxidation. After the oxidation, your silicon layer is there that you can develop using the deposition technique. And then black color is the metal contact, that is how can you develop the contacts, right? So your here is your ion implementation technique can be used to develop the diffusion. You can use the to develop the drain. You can use the diffusion technique, then oxidation process, then deposition technique, then metallization technique, and the etching. All these things you can use. Then annealing at the end. So this is the summary, right? So let me conclude with this CMOS inverter. Let me conclude with this sentence. So step 1, substrate. Step 2, your anvil using the ion implementation. Step 3 is your to development of SiO2 using the thermal oxidation process, right? Then next step 4th is your development of polysilicon using the chemical deposition technique. Then use the etching if required, right? Then development of your uh, drain source using the diffusion technique. Always, so you can while you are using the development of this polysilicon, you can use the lithography, then metallization, and then at the end of the metallization annealing process to check whether is this correct or not. That's all about the fabrications. Thank you for listening. If you have any doubts, please drop your comments here.